Okay. Hi, everybody. This is lecture number 25. We are going to continue discussion regarding the plotting of a three-dimensional surface in a three-dimensional coordinates. In the previous lecture, I have explained to you 4 different ways how we can plot the three-dimensional surfaces or scatter plots. But what we have done in the previous lecture was always by using LabVIEW VI, which is Mesh Grid 2D VI. This is the analog to NumPy NP Mesh Grid function. In this lecture, there is a facility in LabVIEW where we can plot the surfaces with 3 dimensions without using the mesh grid function or mesh grid VI. Fortunately, in LabVIEW, in the mathematics palette, there is a function which is called evaluate y equal f of x1, x2, vi. As you see here, this function gives the output which represents the z value and also outputs 2 arrays representing the input arrays of this function. This function, as I told you, is located at the mathematics palette. Here in mathematics, we go to script and formula and to one-dimensional and two-dimensional evaluations, and there is our function. It is this one. So as you see here, this terminal, which is called y values, is a two-dimensional array. This function, as you see, requires, of course, the input formula, which represents the function, which is going to map the input to an output. And also, it requires to give as an input the names of the variables. In our case, they are called x and y. The limits of the variables at the input, the starting and the ending values, should be arrays with 2 values, one representing x value, initial value of x, and the initial value of y as a lower or starting lower end value or starting value, and 10 as upper value. Of course, this depends on the user. You can write here -2, here -5, here +7, here +8. It depends. But I have selected this regular values because as standard values. So now we have defined the limits of lower values of x and lower values of y, and upper value x and y, lower values and the upper values of x and y. And what do we expect? So we expect here at the output to have a variable which represents the mapping of the input to an output. It is x squared plus y squared. So directly we can take this, in order to plot it, we can take this data and feed it to the surface indicator here. And I told you how to go there to find this in the previous lecture. You need to go to the front panel here, and from the right click anywhere, you will have the palette of controls. You select the graph. From the graph, you go to the three-dimensional graphs, and now you select what you want. If you select a surface graph, you press it and you can put it anywhere you want. Here it is, for example. But for me, it is not necessary. I do not need it now. I will cancel it. So I have plotted here the input and the output. What is there? Something wrong has happened. Ah, okay. This is, I think, because I have put, because of this maybe. If I cancel this, no, there is something wrong happened. What it is, wire has loose ends. Show the error. Here it is. Because when I plotted the network or the grid at the front panel and the terminal was shown here, this display was disconnected. So now I need to cancel it. Now everything is okay. So as you see, all what I have to do is to connect the output directly to plot surface terminal, and here to collect also the x, y initial values and ending values, lower and higher values, and now I can get the figure. Here it is. This is the figure which I have got. So what is interesting, as I told you, there is no need here to use converting of the output to a mesh, or feeding the output to a mesh grid function, and from the mesh grid function, you supply it to the plot surface. No need for that. Directly, this is really an advantage for LabVIEW. Also, I have tried to show you how we can plot a three-dimensional mesh. Exactly the same. I have taken the two arrays representing the upper and lower values of x and y, and I have taken the same two-dimensional matrix which represents the data at the output, and I will get the three-dimensional mesh plot. Here it is. This is the mesh plot of the function x squared plus y squared. Also, I have wanted to demonstrate to you also that if you open or look at this indicator here, you have here an arrow where you can select the mode of operation by using plot helper vector or by using plot helper matrix. I selected plot helper vector. So as you see here the input is an array and the other input is an array. But if I select it as I did here, the plot helper as a matrix, the plot helper as a matrix. So this input should be a matrix, which means that this array must be converted to a matrix. What I have done, I have increased the dimension of the array to 2-dimensional now. And I have increased the dimension here by build array function to 2-dimensional and fed them to the plot helper matrix. Now at the output, I should get the same figure. Here it is, but I have colored it in green, the background here, to show you the difference, just to differ between this figure as a mesh grid and this figure as a mesh grid. They are the same exactly, but I just wanted to color the background to show you the difference. Okay, now we go back. Knowing this fact now, that with this function we can directly work without mesh grid. So this gives you an idea that any function here at the input, you can use this virtual instrument to plot any function with 2 variables directly, and not only this function. Remember, we have an idea about Rosenbrock function. I told you, I gave you some information about it, and we have found by using SciPy its optimum or minimum values. Okay, the expression of the Rosenbrock is given here. 1 minus x squared plus 100 multiplied by y minus x squared all r squared. As you see here, there is a coefficient here or a constant multiplier 100, and 1 minus x has a multiplier a. So generally, in a general form, the Rosenbrock has 2 constants a and b. I took a here equal to 1 and b equal to 100. And really, this is a common practice when working with Rosenbrock. So Rosenbrock function now is fed to our VI. The ranges here are changed. I changed them because these are closer to the real limit values of the Rosenbrock. Rosenbrock minimum value minus 5.12 minus 5.12 for x and y, and the plus and the upper limit is 5.12 and 5.12. So I took it minus 5, 5, which is closer or nearer to the real values, real limits of the upper and lower values of the function, not more. As you see here, the number of points of the figure at the output, or of the arrays, of course, are 25. So this matrix now, if you take its size, it will be 25 by 25. Especially, I have done this here. I have took from this matrix a branch and fed it to array size, and I found the sizes. The sizes here, if you go, they are 25 by 25. Why? Because I have selected the array of 25 here. Of course, you can say this is really the default value, but you can change it. If you want more finer presentation and more thicker representation of points, you can add more than 25. You can have it 50, 60, 100, whatever you want. Okay, so now here at the output, what we have the expression or the function of the Rosenbrock. And I fed the Rosenbrock function as a Z matrix to the 3 surface plot. And I have fed also the 2 arrays representing the XY upper and lower limits. And here I shall get exactly the plot of the Rosenbrock. If I double click here, it is. And you remember, I have shown you this in a previous example, which was done differently, of course. It was done differently. Okay, we did it. Here, in this example, also I am finding Rosenbrock plot. I have plotted Rosenbrock, but with using a more universal function or VI, which exists in LabVIEW also. Where it is, what it is called, it is evaluate y equal a, x1 and x2. So there is an addition here, a constant a. What does this constant a represent? This is an array of two values, which represents the constants which are multiplied by x and by y. Here it was 1 and a equal to 1 and b equal to 100. So I put at this terminal here the parameters 1 and 100. And when I put here the expression of Rosenbrock, I have not to include any coefficients. They are included from here. And this is the names of the variables x1 and x2, the same lower and upper values of x and y. And when you feed it to the surface plot, I have got exactly the same answer. So this plot here is exactly the same as this plot here. It is a matter of how you realize it. If you go to the front panel, to the block diagram and right click there and go to the mathematics, to the scripts and formulas, one-dimensional and two-dimensional, here you come to this function. Here it is. It is named, as you see, evaluate y equal f of a, x1 and x2 virtual instrument. If you want to know how we work with it, we go to the help and see here is the function and here is the terminals which I have connected. The new thing here to you is the parameters which represent A and B. Here they are, parameters. They are shown here as a cluster, as you see, of two values in an array cluster describing the parameters. No, yes, the parameters, A and B, yes. Start point here, the end points here, the formula is here, the variables x and a here, and this is the parameters A and B, which I have included. I don't know if there, here is an example, maybe no, there is no example, but there is some illustration for that, showing you that if we have a function of x1 and x2, and there are constants multiplied or used with xa and b, so they are called A, and this A is, for example, A here is equal to 1, and B equal to 2, y equal to 2x2, where it is, let me see where it is 2 here. With A equal to 1 and B equal to a common function of in x1 and x2, the variables A and B stand for parameters. And here is the example. For example, this formula, A multiplied by sinc gamma of x1 plus x2 minus B multiplied by so and so. So here A is equal to 1, B is equal to 2. So in this terminal, I have to include 1 and 2, which I have done really for the which I have done for the Rosenbrock. So here, as you see, this is the cluster, and I have included an element of 1 and an element of 100 because it is here multiplied by 1. This other expression is multiplied by 100. So it gave me exactly the same figure. Okay. While optimizing functions, there is, as I told you, a set of functions which is called the testing functions, standard functions used very often by mathematicians and by data science engineers. One of these functions, famous function, is this function, which is, we shall come to it also in the future again, which is called six-hump camel function. This is the expression of this function. It is somehow complicated. It is denoted by f capital of X. If I go to the block diagram, here it is, f of X, and now the data is included in this terminal. I have fed the function here to its terminal. I have variables there, only x1 and x2. These are the limits which are really close to the limits of the function. In the real function, they are about -3, 3, -3, 3. And now I have done exactly the same as I have done before for the plot surface. And here, if we go to the block diagram, here is the plot, three-dimensional plot of this function. What else we have? Let us go. It seems to me that, okay. Here I have used three-dimensional scatter. I told you if you go to the front panel, to the graph, and to the three-dimensional graph, there is a scatter, three-dimensional scatter plot. You can use it if you want and if it is necessary. I have tried also to make use of it to show you. So I have connected the output, which is the matrix, two-dimensional matrix, to the scatter plot, and the input to the two arrays are the same. And here we have got, this is the function which represents our case. Of course, also you can rotate this function as you want, giving it the angle upon request. And this is the Rosenbrock also the same. One more example for you is the what we call Himmelblaus function. This function is given here. This is the formula of Himmelblaus function. It is there. Here it is at the block diagram. And here its expression. It is a function. All of these functions are functions of two variables. If I disconnect the terminal, this terminal, which represents the six-hump camel function, I disconnected it and connect this function instead. I remove the broken wires. So now I can get at the output here, instead of this figure, I shall get another figure, which is going, if I run it, it is this type, as you see. This is another function which represents our case, the Hamel-Blouse function. What more? Let me show you also if there is something. Yes, it is plotted as three-dimensional scatter also. There is no problem. Yes, it could be. Here is the three-dimensional scattered of this function. To be very close, here it is. It should be upsetted up and down like this. No problem. Okay, so I think now you have a good idea how to plot a surface or a scatter plot with three coordinates systems by using Python and by using LabVIEW. In my opinion, I feel that LabVIEW has more versatility and more easier approaches to do that than Python. Anyhow, now you have both techniques and you can work with any one of them. Now, what we have done, so we have plotted the three-dimensional plots in LabVIEW and in Python, but we have to work with optimization of the two variable functions by using another means in addition to what we have done. Remember, in the previous lecture, we have found the optimum or the minimum value of the convex two variable function by using SciPy. I want to demonstrate to you how we can do that by using the gradient descent. Really, I found that by using a gradient descent, we can explore more facilities and we have more freedom to know about how iterations are implemented step by step and how we can plot the trajectory of the positions of the minimum values beginning from the first iteration up to the last one where we find the minimum. So let us go and begin. Maybe today we shall work with finding the minimum value, and if we have time, we continue. If the lecture becomes long, we could leave that for the coming lecture. So let me open my notebook. Jupyter Notebook Classic. Okay. Now I shall remind you where we have stopped in the previous lecture. So we are here. It is opening. It takes about half a minute. Okay. So if you remember, we have covered this part and we found if you remember, we have plotted this figure and overlaid the point where is a minimum. And also we have plotted the other figure with some modifications and by using rotating angle activities. Now I think we are here to find the minimum of this function by using the gradient descent algorithm. We have already used the gradient descent algorithm to find the minimum of a convex function with one variable. But when working with two variables, we did not do that yet. Today we shall do it now. So here is our function and we have x and y variables. Remember, when working with gradient descent, we always have to define a start point, and at this start point we find the derivative, and knowing the derivative at that point and knowing the step value or the learning rate value, we multiply the learning rate value by the derivative. Here we found a value which is called, the product is called a step, and this step will be subtracted from the initial value of the point. But here we have a point with two variables, so we need to find the derivative in the direction x with the coordinate x and the derivative with the coordinate y. And then multiply each of the derivatives by the learning rate, and then subtracting from the previous value to get the new value. And the new value now will be the new value for x and the new value for y, which represents the new value for the new point. Here is the idea. So at first we have to define the function. The function is defined. It is called f, and the variables which we have x and y. And this is the expression of our function, known to you very well. Now we need to find the derivative of this function because it is of two variables, so we need to find the partial derivations, df by dx, which means 2x, 2 multiplied by x. This is the derivative by x. We consider y as a constant. And the second step, we find the derivative by y, which is 2y, considering x constant. So we have two values, two derivatives, dfx and dfy. Now, we suppose that the starting x value, start x, is assigned to a variable called x, and the starting y value is assigned to a variable called y. And we create a list, we call it history, an empty list, we call it history. This is a step-by-step work. Now, we shall control the iterative process by a number of iterations. So we give approximately a number of iterations which could be adequate, And at the end of these situations, the program will stop. So for I in range, number of iterations. So we have to define the number of iterations. It is defined here as 600. Number of iterations is 600. The learning rate is defined as 0.015. And the starting X and the starting Y are assigned 10 values. So the value of the coordinate X as a beginning is 10, and the value of Y as a beginning is 10. If we look at the, here it is not shown. Yes, here they are shown. If we rotate, I have rotated it. So as you see, Y here begins from 0 to 10. From 0 to 9 is 10. So it exists within 10 and minus 10. And the same thing for X coordinate between 10 and minus 10. So I have suggested that the values as a start values of X and Y will be 10 at the limits. We will begin from the limits. Okay, so now for I in range of number of iterations, which will be 600, as I told you, we begin by finding the derivative of X of xy, which is, as you see, 2x, and we assign this value to a variable, we call it gradient x. And the derivative by y of xy is assigned to a variable called gradient y. And now gradient x will be multiplied by the learning rate, and their product will be subtracted from the value of x to get a new value of x. This is the old value, which was 10. The same thing applies for the y. So we have the gradient by y multiplied by the learning rate, and the product will be subtracted from y to get the new value of y. And now the new values, these intermediate values, we shall use them in the future. So we append them to the list, this empty list, which we have created and called it history. So we will append the value of x, the values of x, and the values of y, and f of xy, which is the value itself of the function, and to the history list. These variables now will be appended to the history. So we ask at the end, now we finish this function, we have to, this function will return x and y and f x of y and the history, because we may need to work with the history. As ranges, as you see, we have limited the x range between minus 10 and 10 with a step of 0.1, and the y range also we have defined it between minus 10 and 10 also with a step 0.1. Now, in order to plot the function in a three-dimensional coordinates with Python, we need to create a mesh grid. So we call from unpy mesh grid and pass these limits to it, x range and y range. And now we will have two-dimensional coordinates x and y of the mesh grid. And now the new value of z will be a function of this capital Y and this capital X. So z is a function, because here it is a function f given a name f. So it is a function now of capital X and capital Y. Now everything is done practically. What do we need is to illustrate what we have achieved. We will ask to plot the figure To plot the figure, we need to create a figure object in Python, plt dot figure. PLT is from matplot library, of course. It is already existing. So PLT, we call the figure function and assign to a figure object. It is now we have created a figure object. We create an axis in this figure. So from this figure, we call add subplot, and we pass the word, the instruction, let me say, projection equal 3D, so that to create a three-dimensional axis. And now we need to plot our function. So from AX, we call plot surface or plot wireframe or whatever, plot scatter if you want. We plot surface, this big X, capital X, capital Y, and capital Z, and we decide which color it will be, cool warm or normal. No problem here. So now we have plotted the function. These values now are well known to us. Now, for the gradient descent to work, as you see, let me make this capital letter, capital or big and size. So for the gradient function to work, the gradient descent, it requires a starting value of the x, we have it. Starting value of y, we have it. Learning rate already defined. Number of iterations already defined. So this gradient descent will give us the x optimal, the optimal value of the x coordinate, the optimal value of the y coordinate, and the optimal value of the function itself, the minimum value, and the history if it is required. So here I am asking the program to print the x optimum and y optimum. If I look here, I will find x optimum and y optimum are these two values. And you remember, they will be equal to 0 for the squared sum of x squared and y squared. They are both 0. The function itself also will be 0. I think I have also printed it. Yes, print f of x optimum, y optimum. It is also 0. And I have asked the program to print the history -1. -1 here is a sliced row from the history, which means the last value of x and y and the function. All this history will have three values now, x and y and the function itself, the value of the function. So I asked to print history with a sliced last value to see it. The sliced last value is the x, the final x, the final y, and the final value of optimization. Of course, this final value of optimization will be exactly the same as the function minimum. Look, they are the same. And this value of x and this value of y, they are also the same. So I have done this just to be sure that they are exactly the same. Now, what is also interesting for us? We need to plot the point where x optimum and y optimum and where the function of x optimum and y optimum on the surface. This needs a scatter plot. So ax dot scatter plot, we pass to the scatter plot x optimum and y optimum and f optimum. We mark it as an asterisk and color it as red. When we look at the figure and run the program, here it is. As you see, it is shown at the x0, y0, and has a minimum value f of xy equals 0. F of xy equal 0. If I rotate it, it doesn't rotate. So let me try to print here, maybe 100%. Mat plot lib notebook. I think now I have to run the program. It has already finished, yes. As you see, the point is not shown here because this is the position. I did not ask the program to show the drawing at a given angle. So this is done by the program itself. So as I can see it, I have to rotate this to a little bit. Yes. Now, as you see, the point, I have. It was seen by you. Yes. So as you see, here is the point shown, which represents the minimum value of the surface. Now, it is not a function, a line, it is a surface at the coordinates x equal to 0 and y equal to 0. This is y, and this is x, xy 0, and z here is also 0. So, as you see, the working with Python and using the algorithm of gradient descent became systematic for you, I think, through studying 2 to 3 examples. Now it became a systematic work, and now you know the steps exactly how to define them. I want to summarize to you these steps again so that it will be kept in your mind. So first of all, you need to import the libraries, the functions, or the modules which are required or you're supposed to be necessary for the program. Secondly, you have to define the function which you are going to optimize. When working with gradient descent, we need to define the expression of the partial derivatives by the variables x and y if we have only 2 variables. Then we have to define the start point for x and for y. And we have to allocate a space as a list to accumulate there the history, which means the intermediate values of x and y and of the function of x and y. Then, when we go down, we shall make use of the gradient by x of x and multiply it by the learning rate and subtract it from the initial value which we have for x to get the new value of x. And the same thing we do with y. And this will go, this is for the first iteration. The second iteration will repeat, And now this new x becomes the old x, and we find the new value of the gradient, again multiplying it by the learning rate and subtracting it from the old x to get another new x. And the same thing applies for y, and this will continue until we finish with all the i's, with all the I values beginning from 0 up to 600. So what we are supposed to find here in the, let me say, the list in the history, there will be about 600 values, 600 lines. Let me try to find it. If I want, I print here. If I ask the program to print, here it is not necessary. Maybe here it is appropriate. Here, print, let me say, history equal to n dot history. And now let us see what we will get. Missing parentheses here. The print I have forgotten to put. Yes. This is the other. And this is additional. Okay, and now let us run it again. Look, these are the values as you see. X, Y, function of xy, x, y, function of xy. And you go there 600 times. And the last one, which I have showed you before, is this one at the end. If we go now and have a look at it, the last one here, how can I show you? This is the 1x, y, z. Y is to the order of minus 14. If you go up there, you will find it here, to the order of minus. This is the last reading of the function, the minimum value. This is the coordinate y, and this is the coordinate x, where the minimum occurs. This is the last value, which is here also. This is the last value of the y, and this is the last value of the x. Of course, this is too much to show in the figure. I am showing you just to be sure to understand what is going inside it. But if you want to know how many there are in the program, there are 600. But if you want to be sure, okay, let us try to have another verifying. If we want to see here, print, for example, length of history. How many values are there in the history? The length of history. Length of history. Okay. So let me call it length. Length equal. Okay. Length. And now let us print it again. What we have got, the length of the history is maybe down, it will be down. The length is 600. So really we have here 600 repetitions, 600 iteration values, 600 values for x, 600 values for y, 600 for the function itself. And these values are moving, changing from the highest value to the lower value until we come to the minimum. If you remember, we have begun with the value 10. So here, the first iteration of x was 9.7. It moved from 10 to 9.7. The y, the same thing. And this is the value of the function. Now from 9.7, it became 9.4. And the other one, approximately the same. And then 9.1 and so on. And it continues decreasing at that point where we come to the exact minimum value. Okay, what I am interested to tell you, the movement from 10 to the minimum value is an interesting thing, and we need to see it by eyes. And the path, how these intermediate values, these 600 values exist on the surface, and how they are plotted there is interesting for us. We need to see it. This will be shown to you in the next lecture, I promise, so that you will feel confident and feel with some happiness that really this is the case. But with this now, I finish this lecture and hope you a nice day. Thank you very much.